Hi there, we are going to do one example together here on page 1. Please note that this entire page involves ionic bonding. So all of the elements are metal, non-metal combinations. And step 1, we are going to predict the ionic structure using the crisscross method. We already know the crisscross method from weeks ago, and this is used to confirm that our answer is correct. And finally, we're going to prove that ionic structure by drawing the dot diagram, also called the Lewis diagram, to again confirm that the ionic structure we predicted is correct. So to do step 1, the crisscross method, I need to locate these two elements on the periodic table and get their ion charges. So put your eyes on these two elements, and based on their column in the periodic table, you can predict their charge. Gallium is going to be a +3, and tellurium is going to be a -2. So if we crisscross these charges down, we are going to get a final ionic formula of Ga2Te3. And this tells me that gallium and tellurium are going to react in a 2:3 ratio. So now what we're going to do is confirm that by using the dot method. So to start the dot method, we need to draw each element's Lewis structure. And a Lewis structure shows how many valence electrons it has. This can again be predicted with the periodic table. So gallium, based on its grouping, has 3 valence electrons. And tellurium, based on its group, has 6 valence electrons. So what we're going to do is we are going to ionic bond these elements. That is going to involve metals losing electrons and nonmetals gaining electrons. So gallium, our metal, is going to donate and give electrons to tellurium. So we're going to show the journey of each electron with an arrow. So 1 electron has moved from gallium to tellurium. Tellurium has to gain 2 to create a stable full octet in its valence level. So tellurium has now gained 2 electrons. It has 8 electrons in its valence level now. I'm going to give it a check mark. Now gallium, however, is not yet stable. Metals have to lose all of their valence electrons. So gallium is not done. It has to lose 1 more electron. So the only solution is to put in another tellurium, which still starts with 6 electrons, and that final electron from gallium can take a journey to that tellurium. So ask yourself, who's stable now? Our gallium is stable because it lost all 3 valence electrons. But is tellurium stable? No, it has 6 valence electrons and it has only gained 1. So it must gain another. And the only place it can get it is another gallium. So we draw another gallium with its 3 valence electrons. Let's take one from gallium, show the journey of the electron down there to tellurium, and ask yourself who's stable now. It is this tellurium. It had 6 and it's gained 2. But are we done? Not quite, because gallium still has 2 valence electrons to get rid of. Maybe you can see that the end is near. What we need is 1 more tellurium with its initial 6 valence electrons. And we can show the journey of these last 2 electrons from gallium to tellurium. So the gallium has now lost 3. It is stable. The tellurium has gained 2, so it is stable. So the beauty here is that we confirmed the ratio that we predicted, which was 2 galliums for every 3 telluriums. Well, that's exactly what happened here. For 2 galliums and 3 telluriums, it's the perfect number of electrons transferred, so everything will be stable. So our final step here is to draw the ion structure of what forms. And so this is showing not the process, but the final structure. So we have 2 galliums, and they lost their valence shell. So we do not show any electrons on it to represent that it lost its valence level. The one thing we do differently now is because gallium is an ion, we are going to show that it's different. To show that it's an ion, we put it in brackets and we put its ion charge on the outside. This is the standard way of showing that a structure is an ion. So there's our two gallium ions. And now we're going to show the tellurium ions. Now, tellurium didn't lose electrons, it gained. It filled its valence shell. So we are going to show its valence shell full with an octet of electrons on all three. And again, because these telluriums are ions, we put them in brackets. The brackets just mean, hey, this is an ion. And the charge is included as well. So this is the process to show the electron transfer in an ionic bond. For this page, you are going to include the process that I've circled, which is showing the journey of the electrons from the metals to the nonmetals. You are also going to show the final structures. Both of those parts are important.